Have you ever wondered why some elements behave very similarly, like how sodium and potassium both react violently with water, while other elements, like, say, helium and neon, for example, wouldn't react at all? A powerful tool in chemistry to understand the elements and their properties is the periodic table. Now, I used to think that this periodic table was just a list of elements, but turns out it's so much more. It's actually a model that organizes these elements in a way that reveals patterns in their properties. But how exactly? Let's find out. Let's start with the basics. Each element on the periodic table is represented by a chemical symbol. Then there is an atomic number, and usually there's also an atomic mass. Now, the chemical symbol is a shorthand way to represent the element. So Fe over here represents iron. Other chemical symbols involve, for example, H for hydrogen, O for oxygen, and so on and so forth. Okay, then you have something called the atomic number that you can see over here. What does that represent? It tells you the number of protons present in the nucleus of the atom. So hydrogen has an atomic number of 1, which means there's only 1 proton in its nucleus. Oxygen has an atomic number of 8. That means there are 8 protons in its nucleus. And it's this number that determines which element it is. Oxygen is oxygen because it has 8 protons. So if you look at your periodic table carefully, you can see that it is arranged in the order of the increasing atomic number. Okay, now you'll also often see the atomic mass listed over there. This number is basically the average mass of that element's atom, based on the different isotopes found in nature. So look, even though each box on the periodic table is small, it is packed with a lot of information. Now let's talk about some of the patterns that we can find. The first major pattern is how the elements are grouped. We have metals, we have nonmetals, and we have metalloids. Most of the elements on the table are metals. And you can see metals are mostly found on the left side of the periodic table. You can see that nonmetals are found here on the right side of the periodic table. And in between them is a zigzag region of elements called metalloids, which have properties in between that of metals and nonmetals. Okay, let's quickly recall what these properties are. So metals are usually shiny, they are solids. Of course, there are some exceptions, like for example, mercury is a liquid at room temperature. But besides that, usually metals are solids. Then they are ductile, which means you can draw them into wires. And they're also pretty malleable, meaning you can hammer them into very thin sheets. Besides that, metals are also pretty good conductors of heat and electricity. All right, let's talk about nonmetals. They are very different. First of all, nonmetals can exist as solids, liquids, or even gases for that matter. And if they are a solid, they tend to be brittle. They are usually poor conductors of heat and electricity, and they usually have a pretty dull appearance. By the way, carbon is actually an exception to all this. I mean, diamond, for example, which is made of carbon, is anything but brittle or dull. So remember, there are always exceptions, okay? Okay, that brings us to metalloids. They fall somewhere in between. So they look somewhat shiny. They are usually somewhat brittle, and they act as semiconductors, meaning they conduct electricity better than nonmetals, but not as well as metals. And these are some of the commonly accepted metalloids. So we have boron, silicon, germanium, arsenic, antimony, and tellurium. Okay, now let's dig a little deeper. To see more detailed patterns, we need to understand how the periodic table is organized. This entire table is arranged into horizontal rows, which we call periods, and vertical columns, which we call groups. Okay, let's talk about the periods. There are 7 periods over here. And as you move across a period from left to right, look, the atomic number increases and the properties of the element gradually change. You go from metals to metalloids to nonmetals, for example. Okay, what about the groups? Groups are especially important because elements in the same group tend to have similar chemical properties. And there are two common ways to label the groups. One way is to just label them 1 to 18, but there's also an older system which uses Roman numerals along with A's and B's. Don't worry too much about them. The point is you might see either one depending on which source you're referring to. Now, since elements belonging to the same group have pretty much the same properties, we like to give names to these groups. So this first group of elements, we call them alkali metals. These include elements like lithium, sodium, and potassium. And what are their properties? Well, alkali metals are usually soft, they are silvery, and they're pretty reactive, as we saw earlier. They react so easily that they are never found in pure form in nature. And that's why they're usually stored under oil to prevent them from reacting with air or water. But of course, hydrogen is an exception. Even though it is written under first group, it's not an alkali metal. It's actually a non-metal. And it behaves very differently from the elements below it. And so this is a good reminder that although periodic table shows us very strong patterns, there are also important exceptions. Okay, on to the next group. We call them alkaline earth metals. These include elements like magnesium and calcium, for example. These metals are also pretty reactive, but compared to alkali metals, they are less reactive. They're also harder than the alkali metals, they are usually denser than the alkali metals, and their reaction with water is also slower than the alkali metals. Okay, and in the middle of the table are the transition metals. This includes familiar elements like iron and copper and gold and so on. Now, these transition metals are extremely important in everyday life, but their patterns are more complex than those of the main group elements. So for now, we'll focus on the clear patterns found on the left and the right edges of the periodic table. So let's move to the far right. Here we find the halogens. This includes fluorine and chlorine and bromine and iodine. Halogens are highly reactive nonmetals, and they're rarely found in pure form. Instead, they're usually found in compounds, especially combined with metals to form salts like NaCl, which is the most common example. And at the far right edge of the table, we find the noble gases. These include helium, neon, argon, and so on and so forth. And noble gases are very different from the other groups we have discussed. They're almost completely unreactive. And now that brings us to the central question. Why are some elements so reactive while other elements so stable? See, so far we mostly described what kind of patterns we find on the periodic table. But now let's talk about why those patterns exist in the first place. So for that, we have to talk about reactivity. What does it mean to say an atom is very reactive? It means that an atom can more readily lose an electron to become stable, or more readily gain an electron to become stable, or it is more likely to share electrons to become stable. And when we say an element is stable, we mean its electrons are arranged in a way that don't typically change. And the most important electrons for determining the reactivity are the outermost electrons, as you can see over here. These are called valence electrons. And if you look at noble gases like helium and neon, they are so stable because they already have a full set of valence electrons. What does that mean? Well, for helium, it means 2 electrons in its outermost shell, and for most other elements, it means having 8 electrons in their outermost shell. This arrangement makes them very unlikely to react. Now, most other elements do not have this stable arrangement. For example, sodium has 1 electron in its outermost shell, and chlorine has 7 in its outermost shell. So these elements will react in ways to try and get that 8 electrons in its outermost shell. For example, if sodium were to lose 1 electron, then look, its outermost shell would end up with 1, 2, 3, 4, 5, 6, 7, 8 electrons, just like neon. On the other hand, if chlorine were to gain 1 electron, then it too would have 8 electrons in its outermost shell, just like neon. So this explains their reactivity. This idea is summarized in what we call the Octet rule. The Octet rule pretty much states that atoms tend to either lose or gain electrons, or sometimes even share electrons, in order to have 8 electrons in their outermost energy level. Now, this is not a perfect rule, and there are, of course, exceptions, but it describes a very common and useful pattern. So, look, knowing the valence electrons is pretty important to understand reactivity, right? And one of the most useful features of the periodic table is that you can figure out the number of valence electrons just by knowing the group. Group 1 has 1 valence electrons, group 2 has 2, group 13 has 3, group 14 has 4, all the way to group 18, which has 8 valence electrons, making them stable. Of course, helium is an exception. It only has 2 valence electrons, but that still makes it stable. And so now we can understand why elements in the same group behave alike. For example, sodium and potassium are both in group 1. Each one has 1 valence electron. That's why both are soft metals that react vigorously with water. Fluorine and chlorine, for example, both belong to group 17. So each one has 7 valence electrons, and therefore they are highly reactive. So these are highly reactive nonmetals. So as we go down the group, the total number of electrons does increase, but the number of valence electrons, that stays the same. That's why they tend to have the same properties. So putting it all together, the periodic table is a model that organizes elements by atomic numbers in a way that reveals the patterns in its physical and chemical properties. An element's position on the table gives us clues about its behavior, including whether it's metal or it's non-metal or whether it's a metalloid. Elements in the same group tend to behave similarly because they have the same number of valence electrons. And reactivity mainly depends on the number of these valence electrons. Noble gases are stable because they have a full set of valence electrons, 8. And the octet rule describes the common pattern that atoms tend to lose or gain electrons or even share electrons, all in order to obtain 8 electrons in its valence shell. So look, the periodic table is much more than a chart. It's a map that helps us understand how the building blocks of the matter behave. And once you know how to read it, you can begin to predict the chemistry of the world around you.